Okay, so continuing our analysis of the quantification of entanglement. So let me write down again the state as in terms of its Schmidt decomposition. Of course, this is for bipartite entanglement. Remember, the Schmidt decomposition is valid for entanglement of a bipartite system. So we've already seen that the number of Schmidt coefficients which are non-zero tells me about the entanglement versus a product state. So if the number of Schmidt coefficients, non-zero Schmidt coefficients, is greater than 1, this implies the state is entangled, and if it is equals to 1, that this implies it's an product state or an unentangled state. But this answers the number of Schmidt coefficients that are non-zero answers a yes no question about entanglement. But let's say we are not interested in just a binary question about entanglement, whether the state is entangled or it's unentangled, but is there a way to characterize how much entanglement is there in a given quantum state? For example, let's consider an case where I have a state psi1 with this is system A, this is system B, and I have it's a normalized state. Also compare this, I have another state which has an equal superposition of 0, 0 and 1, 1. So if you look at psi1, see, most of the times with a probability of 99%, this is 0, 0 state, and with a very tiny probability, this state is 1, 1. So roughly speaking, the state is very close to a product state. I have a very tiny piece of another element in it, and this state, however, has an equal superposition of 0, 0 and 1, 1. So intuitively one might ask the question, which of the above states is more entangled? How do we capture this notion that our intuition that indeed this state, entanglement of psi 2, is indeed greater than the entanglement of psi 1? So it's a really simple problem, and essentially the Shannon entropy captures this thing. So all I need to do is to calculate the entanglement entropy of the Schmidt coefficient. So for example, I have a state, I express it in its Schmidt basis, and I just calculate the quantity called as the entanglement entropy, which is nothing but the Shannon entropy of the Schmidt coefficients. Remember, lambda I square, all these guys square to 1. So indeed, lambda I squares, the set lambda 1 square, lambda 2 square, let's say d is the dimension. This is indeed a valid probability, a discrete probability distribution. So I can define for any probability distribution for a given probability distribution, the Shannon entropy captures the amount of information about the probability distribution, or it the flip side of information is ignorance. It tells you the amount of uncertainty associated with this probability distribution. In other words, if my probability distribution, let me just write down the probability distribution. If one of the piece of ice, piece of 1 for example, is a certain event and rest all are 0, well then each time I know that whenever I am sending a signal, by certainty I am going to receive the first symbol, and the Shannon entropy associated with this probability distribution is equals to 0. So in some sense I already know what's coming along, so there is no uncertainty. The uncertainty associated with the following probabilities is 0. So intuitively the Shannon entropy captures what is the uncertainty associated with a random variable, or consequently when I'm going to get the information about the random variable, how much information I'm going to obtain. So in our case, the entanglement entropy or the Shannon entropy associated with the Schmidt coefficients tells me about the degree of entanglement, or in other words, it tells me about how far from a product state a given state is. So for example, I had a quantum state which was psi 1, and I had a quantum state psi 2, which was an equal superposition. Now when I calculate the Shannon entropy associated with the first guy, this will come out to be almost equal to 0. However, when I calculate the Shannon entropy associated with the second quantum state, which is just going to be the Shannon entropy of the squared of the Schmidt coefficients, that's going to come out to be log 2. So certainly log 2 is greater than some quantity which is almost 0, and you can see that when these Schmidt coefficients are equal, then I get a maximally entangled state. So indeed the Shannon entropy associated with the Schmidt coefficients captures the degree of entanglement. In a system. So for example, as we've already seen, this state over here, this is with both coefficients being 1 over root 2 equal, I get the maximal Shannon entropy, and this is my maximally entangled state of a 2-qubit system. So this was a Hilbert space of dimension 2 tensored into another Hilbert space of dimension 2. So in this A tensored B system of 2 qubits, these are, I have got for example, I can also have 0 0 minus 1 1. I can also have this thing, and I can also have 0 1 minus 1 0. So these four are the maximally entangled states, or they are called as the Bell states. So this was something for the bipartite quantum system. I can similarly extend this notion of entanglement to a multipartite system. So for example, I have a system A, B, C, D, a system of n electrons. And analogously, I'll define something which is a state, a quantum state of this n qubit system, n electron system. If it is a product state, when it can be expressed or factored into a product, and any other state which cannot be factorized in this way is going to be an entangled state. So for example, these are n of them and n of them. So this normalized state, this is an entangled state in a Hilbert space, which is given by the tensor product of all these Hilbert spaces, or in other words, a Hilbert space, a joint space, vector space of n electrons or n qubits, so on and so forth. So subsequently, we are going to see what can we do with entangled states, or is there a quantum advantage to entangled states as compared to the product states.